Okay, now we want to turn to the electrolysis process, and we need to understand first that the electrolysis process is a non-spontaneous. That is, the delta G of the process is greater than 0, indicating that it is non-spontaneous. And in this process we will be using electrical energy input, that is, to drive chemical reactions. Three things we need to review here to understand the electrolysis process. The structure of the electrolytic cell, we'll just make a note. And once we understand the terminology and structure of the cell, then we'll look at the chemistry of the electrolytic process, and then finally work some problems in stoichiometry of electrolytic reactions and predicting how much of a metal can be deposited. Copper plating, a chrome plating, gold plating is some of the terms you've heard in application. Okay, first thing we need to do is look at the structure of the electrolytic cell. There are two kinds of electrolysis in general. The melt electrolysis and aqueous electrolysis, which we'll look at shortly. But we'll begin with melt electrolysis, in which a salt, such as sodium chloride, is heated to its melting point, and we have ions of sodium and chloride moving freely in the liquid. So it contains the, say, sodium ions and, say, chloride ions floating around, like I say, in liquid form. Much better. Now, the electrodes are usually inert electrodes, typically used, or graphite electrodes. Which are connected to a transformer or a battery. Here in the symbology, the short side lines indicate the negative pole of the battery, and here the long side represents the positive pole of the battery. So after connecting, this electrode becomes positively charged. We'll indicate that with a little positive symbols here. And the other electrode connected to the negative assumes a negative charge upon connection. Now, the cations, opposite charges are attracted to this electrode, and the chlorides are certainly attracted to the positive electrodes. Now, at the this pole, sodium will undergo a reduction reaction, because this will take off some of the excess negative charges that are in this electrode. So here we have sodium gaining an electron going to sodium basic standard state and the metal. And so this electrode is the reduction side of the electrolytic process. Now, the chemistry defines what we call the electrode. So this electrode is defined as the cathode, a cathodic reduction in sodium. The other electrode is the oxidation of chlorides, and we'll need two of those in the melt, sorry. We'll go to chlorine in the gas phase. plus a couple of electrons being given up. This is deficient in electrons, so it would tend to remove the electrons from the chloride and force it into oxidation right here. So this is the oxidation side of the electrolytic process. And the oxidation side of an electrochemical cell is referred to as an anode. So we have anodic oxidation. Now, what you will observe in this would, of course, a buildup of sodium metal on the surface of the electrode if this was a melt process, and you would observe chlorine gas being given off at this electrode as a visible indication of the processes. Being formed. Of course, the process would continue so long as we had a quantity of sodium and chloride available for attraction to the electrodes and undergoing the oxidation and reduction process. Now, we need to look at the chemistry of the electrolytic process. Electrolytic process, as I mentioned a few minutes ago, exists as a melt electrolysis, which is the graphic that I just showed you, and we also have aqueous phase electrolysis. Now, in aqueous electrolysis, the salt ions are in competition with water molecules that will also undergo oxidation or reduction depending on the charge of the electrodes. So we have to take that into account and determine from experiment or from if we have a reduction potential table what reaction is dominating at a given electrode, whether it's water or the ions from the salt. Now we'll start with the melt electrolysis to give a simple outcome for electrolysis. We'll begin with the oxidation reduction of sodium. Okay, sodium chloride, when heated to 801 degrees Celsius or 1474 Fahrenheit, will melt. And as such, we have sodium and chloride ions in the liquid phase. Now, in the presence of electrolytic cell, the electrodes that are negative will attract the sodium ion and undergo reduction. That is, sodium ion in liquid phase will gain 1 mole of electrons, 1 mole of sodium ions, and certainly go to basic standard state form of sodium. Chloride will undergo the oxidation by being attracted to the positive electrode, and the chloride in liquid form will undergo oxidation to chlorine gas and 2 electrons given off there. Now, to get the net equation, we need to double the sodium equation to have a balance of charge, and then we can add the two together. And so we get the net cell reaction for the melt electrolysis of sodium chloride. And this is common practice to use melt process to generate chlorine gas and sodium metal in their basic standard state. Sodium in the aqueous electrolysis wouldn't be reduced to sodium. It would react with the water and form sodium hydroxide. So we'll see, and when we look at the aqueous electrolysis, sodium will not undergo reduction, and water will dominate that electrode and produce hydroxides. Now here is a detailed graphic of what we call the down cell that's used in refining of sodium chloride into chlorine gas here, and liquid sodium metal. Here we see the graphite anode, and plus right here will attract of course the chloride, and chloride will of course be oxidized into chlorine gas. At the anode, that is, you have the two chlorides in liquid state going to chlorine gas plus 2 electrons at that. Now the sodium ions would be attracted to the negative electrode right here, or the cathode. I don't see that named in here. Cathode, and undergo reduction. So we'd see sodium ions gain an electron and become sodium metal in their basic standard state, and would capture the liquid sodium here, and later quantities in a laboratory sample. Okay, now we need to take a look at aqueous electrolysis, and in doing so we're going to look at the electrolytic process involving potassium bromide, copper sulfate, copper 2 bromide, and potassium sulfate. Now, in order to understand, we must also compare the oxidation reduction of water with the oxidation reduction of the salt ions. Oxidation involves 2 moles of water to form oxygen gas, 4 moles of hydronium ion, and 4 moles of electrons. Reduction of water is 2 moles of water gaining a couple of moles of electrons, producing hydrogen gas and hydroxides. Now, we begin with the potassium bromide, and I'll show you how this is evaluated. I would suggest starting with a T-table, and one side undergoing oxidation, one side undergoing reduction, like that. Now, to begin with, we need to write the ionization reaction of potassium bromide, showing the potassium ions and bromide ions. Next, construct a T-table, this, and then over on one side, I like to put reduction because metals comes first. Then on the other side, oxidation. And then, if you wish, to remind you that this is the cathode of the electrolysis, and this is the anode of the electrolysis. Then we need to write the reduction reaction and oxidation reactions of the salt ions. Potassium, of course, in water will gain an electron and go to potassium, basic standard state would be a solid, and oxidation of bromide from ions would go to bromine, and that would be liquid's basic standard state plus a couple of electrons. Then we need to write the oxidation reduction reactions for water. the reduction reaction for water, 2H2O in liquid form plus 2 electrons would produce hydrogen gas plus a couple of moles of hydroxides. Right there, and then the oxidation would give us oxygen and gas plus 4 moles of hydronium ions, aqueous, plus 4 moles of electrons right there. Now, in the process of determining which reaction is dominant in this process, you can set up the electrolytic cell and see what is going on in that from an experimental standpoint. If we draw an electrolytic cell and examine the potassium and chloride in aqueous media, what would we see? Okay, if we have the graphite electrodes shown here like this, and we have it connected to a battery as shown earlier, like this, like that. So we've got a competition between the potassium and the water, and on the cathodic side we see a reduction of water. And so as we observe this electrode, what would you essentially see? First, you'd see hydrogen gas being given off in great quantities. You would see a rapid generation of gas, and to prove it is actually hydrogen gas, you also can check for the pH by checking the litmus. And so not only would you get hydrogen gas, but the pH would be basic. That is, red litmus would certainly become blue litmus, and that would be certainly the indicator of a base. On the other side, what we'd see is a cloud of purple liquid being formed around the anode, the positive electrode, and this one would be certainly undergoing the oxidation. And to be certainly more graphic about it, you'd see a kind of a purple liquid being formed around the electrode, which would represent formation of bromine liquid in its basic standard state. So the dominant reactions would be the reduction of water and the oxidation of the bromine. So in constructing the net equation, we write down 2H2O as a liquid plus 2 electrons goes to hydrogen gas plus 2 hydroxide, and then we'd have the bromide going to bromine under oxidation, 2 bromide ion, 2 moles, aqueous, certainly go to bromine, basic standard state, plus a couple of electrons. Well, since the electron numbers balance, we don't have to adjust the quantities of in the reactions. Now we can add those two together, and you can see the net reaction is the formation of bromine, hydrogen, and hydroxides from bromide ions and water. Now, there's another way that you can define which is the dominant reaction other than experimental, if you have a reduction potential table. Here is a table of standard reduction potentials It shows the reduction reaction of various substances, and on this side it gives what is known as the reduction potential for each of the reactions. And we'll talk about this more and where those numbers come from when we get to the galvanic process. But in here you can find the potassium, and you can find the water reduction potentials and copper and so forth. And here is the water reduction right here. A little further down you can find the here's potassium up here, way up here at the top, and pretty much and here's copper, and right here there's your copper. There's bromide down here. Where is it? No, right here, sorry. Yeah. Okay, here is potassium, then here's your reaction for water, your copper, there's your bromine, oxidation, reduction, right here, and then there's the water oxidation reduction right there. Okay, now I've taken and written down each of the reduction potentials for the reactions from the reduction potential table, and what you need to remember is that on the reduction side, or the cathode, what you're looking for is the more positive value, which dominates the reaction, and on the anodic side you're looking for the more negative reaction up here. So you see this one is a little more close to the zero negative direction. So over here at the cathode again, you're looking for the more negative, more positive positive value dominates, and on this side the electromotive force, or the reduction potential, would be the more negative value. So we'll use this idea in working through the next oxidation reduction sequence that we'll go. Okay, now let's look at the aqueous electrolysis copper sulfate here, and again we need to start with the ionization. Copper sulfate as a solid, we put it into aqueous phase. We'll make copper 2 ions, aqueous, plus the sulfate ions, aqueous. Now the oxidation reduction of copper, and then oxidation reduction of sulfate, and then we'll compare those with the oxidation reduction of water and see how who's dominant at what electron. So we take each one, we build a T-table again for reduction and oxidation, and put your reminders here to help you remember what is going on. The cathode, and we're looking for the more positive reduction potential, and so that would mean the copper would dominate in this one. And then over here we look at the more negative, and so the looks like the water is dominating in this one. So we can mark those. I just put a dot here. This one's dominating, and of course that one's dominant. So we'll write those two reactions and add them together to get the net reaction. So we'll start with the copper plus 2 plus a couple of electrons goes to copper metal, and then the water, 2H2 H2O will go to O2 gas plus 4H plus 4 electrons. Now in this case we will have to double this, and then we can add this together to get the net reaction. So here is the net reaction for the electrolysis of the copper sulfate. Now one of the things you can look for experimentally is that you can test the solution next to the oxidation side, or the anode, and you'll find it will turn red litmus to, blue litmus red, excuse me. And so you can test for presence of acid, and you can also see the generation of oxygen gas in the reaction. So here we have the metal ion of the salt dominating, but in the other electrode, the anode, we find water will dominate. Well, in the next one, the copper bromide, we'll look at that, and we'll find both ions of the salt will dominate. So now we want to look at the aqueous electrolysis of the copper bromide, and again, copper bromide as a salt, and water will ionize to copper 2 ions and a couple of bromide ions, and then they will undergo the oxidation reduction, and we'll jot those down in a T-table. Look at the reduction potentials and determine which one's the dominant at each. Okay, so constructing the T-table, we want to look for the more positive electrode potential in the reduction side, and the more negative electrode potential in the oxidation side. So here is, we'll take copper first if you wish. So copper plus 2 plus a couple of electrons will go to copper solid, and then the oxidation of the bromide to bromine goes to Br2 as liquid plus a couple of moles of electrons. Like that, water reduction goes to hydrogen gas plus 2 moles of hydroxide aqueous, and then 2 moles of water will go to O2 gas plus 4 moles of hydronium plus 4 moles of electrons. Well, and then we put in the reduction potentials. This one is a plus 1.23 volts right there. Here is a minus 0.83 volts right there. Now the copper is 0.34 volts, and the bromine, let's see, 1.07 volts. Okay, so we're looking for the more positive value here. So it looks like the copper will dominate, and the more negative will be the 1.07. So both the ions of copper bromide will dominate, and the water does not enter into the process. So we will pick the copper, and it goes to copper solid, and then the bromide to Br minus in solution will undergo oxidation to bromine as a liquid plus a couple of electrons like that. The charge balance is 2 electrons, so now we can add them together, and we have copper plus 2 aqueous, if you put states in, plus 2 bromides aqueous will go to bromine I'll put the copper first. Copper plus the bromine as liquid. And so now you have the net reaction for that one. Okay, now the last one I want to do is sodium sulfate. And in this one, neither of the salt ions will dominate, and both the water oxidation and reduction dominate. Okay, again, we start with the ionization of the salt in water, and of course that's sodium sulfate as a solid, and in water, put it up to H2O. Right there goes to a couple of sodium ions, aqueous, plus the sulfate ions, aqueous, also. So again, we construct our T table, put our reminders down if we so wish, and we enter the oxidation reduction of each of the ions as well as water. We'll start with water this time, to H2O as a liquid, plus a couple of electrons will certainly go to hydrogen gas, plus a couple of moles of hydroxide, aqueous. Then sodium, plus one electron will go to sodium. Basic standard state would be a solid. Over here, the oxidation of water goes to oxygen gas, plus 4 moles of hydronium ion, plus 4 moles of electrons, like that. And so the sulfate, SO42 minus, aqueous, goes to S2O8, 2 minus, aqueous, plus a couple of electrons, like that. Again, oxidation potentials for. Okay, so here are the reduction potentials for each of the oxidation reduction reactions. So what we're looking for at the cathode is the more positive number. Sorry, I needed to put a negative in there for sodium. Anyway, here we're looking for the more positive, which would be the water reduction, and here the more negative would be the water oxidation. And when we compare those values, now we add them together. So we'll take the 2H2O as liquid, plus a couple of electrons, 2H plus 2 hydroxides, aqueous, right there. Then 2H2O liquid, 2O2 as a gas, plus 4H plus aqueous, plus 4 electrons. Now, of course, the reactions do not have a charge balance, so we need to double this reaction here. So I'm just going to bring it down here to keep from scribbling all over the plate here. And so if we double, we get 4H2O liquid plus 4 electrons, and that goes to 2 moles of hydrogen gas and 4 moles of the hydroxide, like that. So first thing is we can cancel the charge of 4 electrons on each side. Then we'll add everything together. Well, this shows 6 moles of water on the reactant side, and this goes to 1 mole of oxygen gas plus 2 moles of hydrogen gas, like that. Okay, plus 4 moles of hydronium ions, plus 4 moles of hydroxide. Well, this is going to combine very quickly hydrogen and hydroxide into 4 moles of H2O, and as a result this will cancel with this and simplify the equation to 2H2O as a liquid. We'll undergo electrolysis to produce a mole of oxygen plus 2 moles of hydrogen gas. And this is a common and very popular way to produce quantities of oxygen and hydrogen for laboratory purposes, as well as oxidation reduction, generate hydrogen and oxygen for fuel cells. So that pretty much completes the chemistry of the electrolysis process. Now, so next we need to look at the analytical process for mathematics or stoichiometry of electrolytic process.